Welcome back. At the end of the last class, I said that the equation estimated by Linus using multiple regression can be used to predict outcomes in next summer's rally. Today, I'll show you how. However, I need to make a few qualifications. First, for the equation to be useful, the population from which next summer's riders will be drawn must be substantially similar to the population that last summer's riders came from. That means they should be entering 9th or 10th grade in the fall and train with riding clubs similar to the apples, oranges, and grapes. And of course, we'll need to know the riders' GR and GE scores. The second qualification is this. It's important to recognize that predictions using the equation are somewhat uncertain and must therefore be expressed in terms of probability. The first source of uncertainty is what we call sample size. The equation is based on results for only 30 riders, and we don't know how representative they are of the population from which next summer's riders will be drawn. If 30 different riders had participated last summer, Linus would likely have produced somewhat different estimates for the coefficients and the constant. The second qualification is that the equation only explains 77% of the variation in M. This means that it is incomplete. There may be other factors that explain rider performance that we haven't considered. And of course, random chance also plays a role. Weather conditions, illness on the day, or a flat tire. This is why the equation includes the error term E. The red lines on this chart between actual values of M and the values predicted by the regression are measures of E in our data set. Now, despite these uncertainties, the regression equation provides a workable model for predicting the probability of rider outcomes next summer. To get started, we need to think of the variable M, the miles a rider will cover next summer, as a random variable. A random variable is one whose value on any one trial is not entirely predictable. For example, the outcome when you roll a die is a random variable. What is certain is that you will roll a 1, a 2, a 3, a 4, a 5, or a 6. What is uncertain is which it will be, but we know that the probability of each possible outcome is 1/6. I will now roll a die 10 times and make a chart of the outcomes. This kind of chart is called a histogram, also known as a frequency distribution. The 6 possible outcomes from the roll of a die are shown on the x-axis. The y-axis shows the number of times each outcome is observed after 10 rolls, or trials. Here, for example, we see that a 6 was rolled 4 times. Now, to me, the histogram looks pretty random. However, after 100 trials, the frequencies look more uniform, although there is still significant variation. I rolled a 2 and a 3 14 times, and I rolled 4 22 times. But after 1,000 trials, the frequencies are beginning to even out. The least frequent outcome was the 5, which I rolled 156 times, and the most frequent was the 4, which I rolled 174 times. Since the probability of each outcome is the same, after enough trials, there will be hardly any variation at all among the 6 frequencies. Now, suppose that instead of rolling only 1 die, I roll 2 dice on a single trial and count the sum of the 2 as the outcome of that trial. There are now 11 possible outcomes ranging from 2 to 12. The probabilities of these outcomes are not the same. Double 1 is the only combination of the dice that results in a 2. Double 6 is the only combination that results in 12. But there are 6 combinations that result in a 7. So here's the frequency distribution after 10 of these 2 dice trials. It looks pretty random, and when I repeat the exercise 10 times, the 10 distributions are all over the place. Let's now look at histograms showing the results of 100 trials. Again, I'm doing the 100 trials 10 times. These 10 histograms are more regular, and the higher frequencies are somewhat concentrated around the center. Finally, here are 10 histograms showing the results of 1,000 trials. By the way, don't imagine that I'm sitting here rolling 2 dice all day long. It takes Excel only a few seconds to produce 10 histograms of 1,000 trials of the sum of 2 dice. The bell shape we see emerging here is a shape of what in statistics is called a normal distribution. And this illustrates one of the most interesting facts in all of statistics. When a random variable consists of the sum of 2 or more other random variables, the distribution of multiple trials of that random variable will be normal, which is to say, bell-shaped. The central value of a normal distribution is the mean value, which is also called the expected or most likely value. When the variable is a sum of 2 dice, the mean or expected value is 7. That's because, as I said earlier, the sum of 7 results more often than any other combination when we roll 2 dice. So, what does all this have to do with predicting values of M for next summer's rally? A minute ago, I said we should think of M as a random variable. But actually, M is the sum of 5 random variables. These are the 5 terms in our regression equation. The first 3 terms are GR, GE, and IN, each multiplied by a coefficient. The 4th term is the constant K. These 4 terms are random variables because A, B, C, and K were estimated by Linus looking at the results for only 30 riders. And as I said a minute ago, Linus would have estimated somewhat different coefficients if last summer's riders had been different. And this means that each parameter in the equation, A, B, C, and K, is uncertain. And this means that these 4 terms of the equation are random variables. Then there's the error term E, which represents the 23% of variation in M that is not explained by GR, GE, and IN. E is a random variable by definition. There is no way to predict what the value of E will be for any given rider. So now that we see that M is the sum of 5 random variables, we should not be surprised to see that the histogram of last summer's results is somewhat bell-shaped. And if there had been 1,000 riders rather than 30, the histogram would be even more bell-shaped. In our next class, we'll use the normal distribution to predict the probability that Gina, who trains with the Apples, will cover at least 35 miles in next summer's rally. The key to this is to understand that a frequency distribution can also be thought of as a probability distribution. I'll see you next week.